next I would like to spend some time on a very fundamental result, namely that under certain conditions, which I will spell out, it doesn't matter which ensemble you use to describe a fluid. And this gives a big practical advantage, because when you want to describe the thermodynamic properties of a fluid, you have different possibilities. You can decide whether you take the canonical ensemble or the grand canonical, and you are free to choose whichever is more convenient for calculations. Right? When you know that they are equivalent, they make identical predictions about the thermodynamic properties, then you are free to choose the ensemble that's most convenient to you for your calculation. The prerequisites, the requirements that must be met are all the aspects of the thermodynamic limit. These include the aspects that we have already discussed: homogeneity, stability, and then as a further aspect we will need that the size of your system, typically characterized by the particle number n or also by the volume, the size of the system is very large. When these conditions are met, then I claim that all ensembles, so the microcanonical, canonical, or the grand canonical ensemble, all these ensembles are equivalent in the sense that they give the same predictions for the thermodynamic properties of your system. And just an important exception, though, are fluctuations. So they make the various ensembles, they make different predictions and statements about fluctuations. So when you want to calculate variances that we had looked at last week, then it does make a difference which ensemble you use, but for all other properties, the choice of ensemble does not matter. Now, as I said, this is first of all a major practical advantage, because you can simply choose the ensemble for which the calculations are easiest. The fluctuations are an important caveat that I already mentioned. Another caveat is it's really important that you do have stability. So all three conditions that are listed on the left-hand side are important. You will also see that when we prove that statement mathematically. But in particular, when you are at a phase transition, then the system becomes unstable. You may have coexistence at the same time of different phases. The system is no longer homogeneous, and the homogeneous phase is not stable anymore. So then some of these prerequisites break down, and as a consequence, ensembles are not equivalent anymore. So let me also add the caveat here on the left-hand side that this may break down at phase transitions. In order to prove the complete equivalence of all three ensembles, of course, you have to prove the equivalence of microcanonical with canonical and of canonical with grand canonical. I will focus on one of these equivalences. I would like to argue that the canonical and the grand canonical ensemble are equivalent. Let us consider as a starting point the grand canonical partition function. Remember that the grand canonical partition function is a function of the inverse temperature, the Lagrange parameter alpha, its conjugate to particle number, and the volume. And it's given by the trace of e to the minus beta times Hamilton operator plus alpha times particle number operator. Now this trace is defined in a Hilbert space in which particle number is not fixed. So we are in a Hilbert space that contains states with arbitrary particle numbers. This Hilbert space is composed of subspaces. In each subspace you have a fixed particle number. So Hn, this curly Hn, is a Hilbert space that contains states with all states with fixed particle number n. Such a Hilbert space is a subspace of the entire Hilbert space that we are considering. We have our Hilbert space with variable particle number contains many subspaces, sub-Hilbert spaces if you wish. In each subspace you have a fixed particle number. And the particle number in principle can vary between 0, you can have no particle at all, and you can have up to infinitely many particles. So when you glue together these various n-particle Hilbert spaces, and you let n go from 0 to infinity, then in this way you can build up your full Hilbert space that contains states of arbitrary particle number. The mathematical symbol, or the mathematical operation that one uses the direct sum of these Hilbert spaces, and the direct sum goes from n equal to 0 up to infinity. Now, intuitively, you can view that as gluing together subspaces to a larger Hilbert space. So this is in the grand canonical ensemble, this is the Hilbert space that we are working in, and this is the Hilbert space in which the trace in particular is defined. We can express that with traces in these subspaces that correspond to fixed particle number. We can say this is the trace of this exponential in a Hilbert space corresponding, in a subspace corresponding to fixed particle number. That's why we give a subscript n to this trace. So this trace here is in the Hilbert space Hn with fixed particle number. But then we have to add, we have to take the sum over all possible particle numbers going from 0 to infinity. When we are in a Hilbert space with fixed particle number n, then of course all states in this Hilbert space are eigenstates of particle number with corresponding eigenvalue n without a hat. So in this subspace with fixed particle number, we can treat the particle number operator like a number. We can replace, in that subspace, we can replace the particle number operator by the eigenvalue n. So in this exponential, we can replace n operator by n eigenvalue. And then we have e to the alpha n, that's just a C number. It's just a factor that we can take in front of the trace. So we can write that as e to the alpha n, now without a hat, because it's the eigenvalue. And we have the trace e to the minus beta h. So we've taken the e to the alpha n out of the trace, in front of the trace. Now we have the sum still to consider. But what is this? What is the trace? What is this trace here? That's the canonical partition function. So this is nothing but the canonical partition function, which is a function of beta, inverse temperature beta. It's a function of particle number and of volume. And to make this distinction very clear between the grand canonical partition function and the canonical partition function, I would like to give the grand canonical partition function a subscript G for grand canonical, and the canonical partition function a subscript C for canonical. And you see now that you can, there's a formula that expresses the grand canonical partition function in terms of the canonical partition function. And it involves this infinite sum over e to the alpha n, and then times the canonical partition function. This is mathematically a discrete Laplace transform. So the grand canonical partition function is the discrete Laplace transform of the canonical partition function. This formula is that I showed you on the previous page is general, but now let's look at consequences of the thermodynamic limit with the three aspects that I had listed before, and see how this helps us in evaluating and working with this general formula. Let's first look at homogeneity. Homogeneity implies that the log of the canonical partition function, in fact the log of any partition function, but in particular also of the canonical partition function, is extensive. We had discussed this before. This in turn implies that when I divide by the volume, so I take 1 over the volume log canonical partition function. The volume is also extensive. Now the ratio of two extensive quantities is intensive. So this ratio then is intensive. Now let me introduce a new variable. Let me introduce the variable little x, which I define as the particle density. So this is n, particle number n, over volume v. That's the particle density. And x is also an intensive variable. Now we have the left-hand side, which is an intensive quantity. It depends, in principle, it depends on inverse temperature beta, particle number, and volume. It's a function of beta, particle number, and volume. We can also instead write this is a function of beta, particle density x, and now possibly others. Because we had on the left hand side we have three variables on which this depends, beta, n, and v. On the right-hand side, so far we have only two. We have beta and x. But in fact, these two suffice. There are no more. In fact, this is already it. It depends only on beta and x. This is because of the Gibbs-Duhem relation, which is also a consequence of homogeneity. The Gibbs-Duhem relation says when you have a homogeneous system, then, and you have three intensive variables, then they are not independent. If you have three intensive variables, then one of them is a function of the other two. And this applies here as well. We have on the left-hand side, we have an intensive quantity, something that's intensive. On the right-hand side, we have two intensive variables, namely beta and x. They are both intensive. Gibbs-Duhem says that whenever we have three intensive variables, they cannot be independent. One of them must be a function of the other two. And therefore, here, Gibbs-Duhem tells us that the left-hand side must be some function of beta and x only. This is the first consequence that follows from homogeneity. So next we look at the consequences of the fact that the system must be stable. Now this has an implication for the second order derivative of this new function little f, derivative with respect to x. Remembering the definition above, this is nothing but v times the second order partial derivative with respect to particle number of the log of the canonical partition function at fixed temperature and volume. Now, previously we had studied the log of the canonical partition function as a function of volume at fixed particle number and inverse temperature. We had discussed that this function must be concave and that hence its second order derivative with respect to volume must be negative. Now you can repeat exactly the same argument that we had before in the context of stability and argue that also the second order partial derivative with respect to particle number must be negative. So also when you consider the log of the canonical partition function as a function of particle number at fixed volume and inverse temperature, then this must be concave too. So this is concave. And as a consequence, this second order partial derivative must always be negative. So this follows the same reasoning as in the case where we showed ultimately that the compressibility of the system must be non-negative. So as in the case of investigating the compressibility. Only that now we've exchanged the roles of volume and particle number, but the logic is exactly the same. So we know that this little f is a concave function of x. And now we look at the limit where we let the size of the system go to infinity. First of all, we can then consider little x as practically a continuous variable. Strictly speaking, x is n over v. N can only change in discrete steps of 1. You have only entire particles. So also x, in principle, at fixed volume, of course, x varies in discrete steps. But if the size of the system goes to infinity, then effectively you can regard x as a continuous variable. A further consequence is that the discrete Laplace transform that we had on the previous page, the formula for the grand canonical partition function, this was the discrete Laplace transform of the canonical partition function. We can replace now the sum by an integral over x. We can now write the grand canonical partition function as a function of beta, alpha, and volume now becomes volume times an integral from 0 to infinity dx. Then we had there an e to the alpha n in this discrete Laplace transform. The n we replace by x times the volume. So we have an e to the volume alpha x. And then we have the canonical partition function, which we can write as e to the log of the canonical partition function. And the log of the canonical partition function we write as volume times this function little f. So effectively we have here in the exponent a plus volume times function little f, but the volume we can take outside the bracket, and then we have the function f of beta and x. So in this infinite size limit we can replace the sum by this integral. Now we know from stability that little f is a concave function. This means strictly concave. This means that the first derivative of f, so f primed, monotonically decreases. Yeah? So x is in this integral, x is in the range between 0 and infinity. At x equal to 0, this function has some slope, some f primed at 0. And this is larger than f prime at x larger than 0. So this f prime is monotonically decreases. Or in other words, minus f prime, minus the first derivative, monotonically increases. Now let us choose the alpha in the range where it is between the derivative f prime minus the derivative f prime at x equal to 0, and it's smaller than minus f prime at x going to infinity. Yeah, we know from concavity that this upper limit minus f primed at infinity is indeed strictly larger than minus f primed at x equal to 0. And alpha is restricted to be between these two bounds. When we make this choice for alpha, somewhere in this range, then we are guaranteed that there exists an x naught, some value for x, somewhere in the range between 0 and infinity, at which the exponent of the exponential that features in the integral, the exponent has a maximum. So with this choice of alpha, there exists, and in fact it's a unique x0 larger than 0, at which the exponent has a maximum. If you make this restriction for the range of alphas, then you are guaranteed, you take the first order derivative of the exponent, that's alpha plus f primed, that's the derivative of the exponent. You have an extremum if alpha equals minus f primed. Now, if alpha is in this range that we have chosen, then, and since the function f is concave, and therefore this minus f primed is monotonically, strictly monotonically increasing and also continuous, then there must be some value for x at which you have equality, at which minus f prime is equal to alpha. And this is, that's a unique value, because it's the monotonic increase of minus f prime is strictly monotonic, so there's a unique value x0 at which you have equality, at which alpha equals minus f primed at this x0. And at that point you have an extremum for the exponent, and since the function f is concave, it must be a maximum. Now, around this maximum, we can Taylor expand the exponent around this maximum x0, and then we find that alpha x plus this function f of beta and x is alpha x0 plus f of beta x0, 0th order. Then comes the first order, but this doesn't contribute because at the maximum the first derivative vanishes, and the next order that contributes is the second order 1/2 f double primed at beta x0 times x minus x0 squared. And though maybe for those of you who are more mathematically interested, this Taylor expansion of the exponent up to second order then amounts to a saddle point approximation for the exponential. Now let's see where we stand. We still have a formula for the grand canonical partition function. We have already approximated the discrete Laplace transform by the integral, and now we can approximate the exponent in the exponential that features in the integrand. We can approximate the exponent by its Taylor expansion. Then the 0th order term in the Taylor expansion we can separate out and take in front of the integral. These are the factors e to the alpha x0 v and e to the v times this function f evaluated at x0. These two factors that are the 0th order terms, or come from the 0th order term in the Taylor expansion, we can take in front. We also have a factor v in front of the integral, And what remains is an integral from 0 to infinity dx. And then we have e to the 1/2 times volume times the second order derivative of the function f at the extremum. Now we learned that this second derivative is strictly negative. So we can replace it by minus its absolute value. And then we have an x minus x naught squared. Now you see that this has the form of a Gaussian distribution. This is proportional to a Gaussian which is centered at x naught and which has a variance proportional to 1 over volume, or standard deviation proportional to 1 over the square root of volume. So it has, in other words, it has a width of order 1 over square root of the volume. And this means, of course, that as the system becomes larger, and this is the limit that we are looking at, the thermodynamic limit, the system becomes very large, the volume V becomes very large, even formally approaches infinity, then the width of this Gaussian becomes smaller and smaller. And we can treat it like a delta function. We can certainly perform this integral over the Gaussian here, and we find that this is, now this remains e to the alpha x naught v, e to the v function at beta and x naught. Then we have our v, and the integral over the Gaussian gives square root of 2 pi over volume times the absolute value of the second derivative of f at x naught. At this point, we can identify, we can go back to writing this here as the log of the canonical partition function as a function of beta, volume, and particle number, for which we have to insert here x naught times v. Let me call this x naught times v. Let me call this n with a subscript c, meaning that this is the particle number that features in the argument of the canonical partition function. And I do the same replacement here. The x naught v, this is the particle number featuring as an argument of the canonical partition function. Finally, we can take, of this whole equation, we can take the logarithm, and we find that the log of the grand canonical partition function equals the log of the canonical partition function evaluated at beta, volume, and the particle number nc, plus alpha times the particle number nc, plus, and then we have the log of the rest. We have this factor of v times this big square root, the log of that. Well, the v's partially cancel, so we have there a log of 1 over the square root of v. So this is a term which is of the order logarithm of the volume. And then we have a log of this, the remaining factors, 2 pi, and this absolute value of the second derivative. These are all intensive. So they don't scale with volume, they don't scale with size. And therefore, they are, I write this here as order 1, meaning that they don't scale in any form with the size of the system. The contribution before, that scales like the log of the volume, so it scales like the log of the size of the system. And the remainder is just a constant that doesn't scale with the size at all. Now, when you look at the large size limit, you know the logs of the partition functions, they are extensive quantities. So they scale linearly with the size of the system. This log of the partition function, the other log of the canonical partition function, and also the alpha times particle number, they are all extensive, so they scale like the size of the system. Okay? In contrast, the other two terms, they scale at most with the log of the size of the system. So when you let the size of the system go to infinity, they grow much more slowly than the terms to the left of this vertical line. So in fact, as the size goes to infinity, these terms here dominate, and these terms become negligible. And hence you can say that as in the thermodynamic limit, where the size goes to infinity, you have this relationship here between the log of the grand canonical partition function and the log of the canonical partition function. They differ by alpha times the particle number. We are not yet at the end of the argument. Amongst other things, we still have to prove that the particle number n with the subscript c, so the particle number entering in the argument of the canonical partition function, is the same particle number that you would obtain from the grand canonical partition function. This is what we are going to look at next. So what we have yet to show is that the grand canonical particle number, which we obtain from the grand canonical partition function by taking the partial with respect to alpha, that this is actually the same as the canonical partition function, which we had simply defined as the argument of the canonical partition function, namely, and that was this product x naught, where the maximum lies, times volume. So this equality we have yet to show. To this end, let's start again from this formula for the grand canonical partition function. That was volume times this integral from 0 to infinity, dx, and then e to volume alpha x plus this function f. When we take the partial derivative of this with respect to alpha, then we get the same exponential back, and the inner derivative is x times the volume, and then times the same exponential. Now, as before, we can approximate the exponential by a Gaussian. We can do the same Taylor expansion as before and write this in the form e to the alpha x naught volume, e to volume function evaluated at x naught. Then we have the volume still, and then we have the integral from 0 to infinity dx x times v times now a Gaussian. And we know from before this is peaked at x naught, and the width is of the order 1 over the square root of the size. So the width becomes very small. So the width goes like 1 over the square root of the volume, square root of the size. Then let's look at the partial derivative with respect to alpha of the log of the grand canonical partition function. This is 1 over the grand canonical partition function times the partial of the partition function with respect to alpha. For the partial of the partition function with respect to alpha, we have the result on the previous line. It's these prefactors, and then we have an integral over x times v times a Gaussian. And then we divide that by the canonical partition function, which has the structure, it's the same prefactors, and then basically the normalization of the Gaussian. So this ratio gives you the expectation value of x times v, the expectation value evaluated with this Gaussian distribution. The Gaussian distribution, though, we know, is peaked at x naught and very narrow. Its width scales like 1 over the square root of the size, so it's practically in the large size limit, practically a delta function. So this expectation value of x times v with this Gaussian is actually equal to x naught times v, up to corrections of the order 1 over the square root of the size. The corrections of the order 1 over the square root of size, they relate to the expectation value of x. Now we are multiplying this with v, so when we relate this to the entire expression here, then we should say this is up to the order of the square root of the size. But still this is fine because the particle number itself scales linearly with the size of the system, but the corrections scale only like the square root of the size, so much slower, and therefore the relative size of these corrections becomes smaller and smaller as the system becomes larger. To be complete, you should also show that not only the expectation values or the predictions for the particle number are the same, but also the predictions for the energy are the same. So likewise, you must show that the internal energy that you obtain from the grand canonical partition function and the internal energy that you obtain from the canonical partition function, that these are equal to. Now this one here on the left-hand side you obtain from the log of the grand canonical partition function by taking minus the partial with respect to beta, and you obtain on the right-hand side the internal energy by taking off the canonical partition function minus the partial also with respect to beta. In the left case, this is at constant alpha and volume, and on the right this is at constant particle number and volume. So this you should also show, that also the energy expectation values are the same. And you can proceed exactly with the same logic as above. Again, you start from the grand canonical partition function, this formula with the integral, only that then you take the partial derivative with respect to beta, and then following the same reasoning as above, you find that the partial with respect to beta of the log of the grand canonical partition function, that this is volume times the partial of this function little f with respect to beta, and of this product you take the expectation value in the Gaussian. And you use the same argument. You say this is a very narrow Gaussian, it's peaked at x naught, its width is very small in the large size limit. So I replace this by, or this gives volume times this partial, simply evaluated at x naught. But then you remember that the function little f is nothing but 1 over the volume times the log of the canonical partition function. So this is nothing but then the partial with respect to beta of the log of the canonical partition function. Again, up to corrections that scale only as the square root of the size of the system. So you find with the same logic that the log of the grand canonical and the log of the canonical partition function have the same partial derivative with respect to beta, up to corrections that become negligible in the large size limit. And this is exactly what you needed in order to show that they give the same values for the internal energy. So up to this point we have shown 3 things. We have shown, first of all, on the previous page, we've found a simple formula that relates the log of the grand canonical partition function to the log of the canonical partition function. And then on this page we have shown that both partition functions give the same values for particle number and internal energy. We're still missing one final piece of the argument to really show that the 2 ensembles are equivalent. Let me start from the relationship that we had derived between the log of the grand canonical partition function and the log of the canonical partition function. They were related by alpha times n, so they differ by alpha times n. And now at this point I can omit the subscript c that I had previously, because we have shown in the meantime that both ensembles give rise to the same particle number n, and therefore we no longer have to distinguish between ng and nc. We simply call both now n without a subscript. What we have yet, and this is the last quantity that we have to look at, what we have yet to investigate is how the entropies are related. The entropy that arises from the grand canonical ensemble can be calculated from the grand canonical partition function with the usual formula, that's k times the log of the grand canonical partition function plus k beta u minus k alpha n. But we just saw that log of the grand canonical partition function minus alpha n, due to the formula above, this is equal to the log of the canonical partition function. And then we still have the k beta u. But k times log times the canonical partition function plus k beta u. And here again, we no longer have to distinguish between the canonical u and the grand canonical u. We showed on the previous page that they are the same. So we omit the subscript. So this here, this last sum, this is nothing but the entropy that we obtain from the canonical partition function. So the entropies are the same. The resulting entropies in both ensembles are identical. So we find same particle number, same energy, same entropy. Volume is the same anyway. It's all the same. So in particular, we have at same volume, same particle number, same energy, we have in both ensembles the same entropy. And this implies that we must have in both cases the same functional dependence between entropy and its natural variables. So we must have in both ensembles the same function S as a function of u, n, and v. But we said earlier that whenever two systems or two models give the same functional dependence between of the entropy on its natural variables, then they are thermodynamically equivalent. And that's what we have just shown. That completed the proof. When we know that they have same u and v and also then the same entropy, this means there's the same dependence of entropy on its natural variables, and this guarantees that thermodynamically they are equivalent. So both ensembles will, as a result, predict the same thermodynamic properties. Again, with a caveat up to fluctuations. And that's precisely what we wanted to show. That completes the argument why the two ensembles in the thermodynamic limits, homogeneous, stable, and infinite size, they give rise to the same thermodynamic properties. Just for completeness, I would like to add here once again the warning that as soon as the second order derivative of this little function at x0, this becomes 0 or very close to 0. And this is precisely what may happen at a phase transition, and what we are going to investigate later. So as soon as this happens, this second order derivative becomes approximately 0, then the above argument can break down, and we can find differences between these two ensembles. And that's simply because at phase transitions we will see that fluctuations play an important role. Fluctuations become large, and then you can no longer assume blindly this equivalence of ensembles. Okay, but leaving this aside, when the assumptions are satisfied, we have shown the equivalence. The equivalence of ensembles allows us to draw another of these nice Guggenheim squares. It looks as follows. I write in one corner I write the log of the grand canonical partition function. In another corner, I write the log of the canonical partition function, and in yet another corner I write S over K, and later on I will add something to that. But for the time being, I'll leave it at that. Oh, and then I draw the arrows, and on the sides of the Guggenheim square I have alpha, beta, particle number, and internal energy. And throughout, I keep the volume fixed. All functions in the corners of the square, in addition, also depend on the volume. But I'm not spelling this out, I'm not writing this down explicitly. They all also depend on the volume, and I keep the volume fixed. And from this Guggenheim square, we can again derive a number of relationships. And it works the same way as the previous Guggenheim square that we had seen. First of all, each corner is a function of the adjacent sides. So each corner has as its natural variables the adjacent sides. Let's check it. The grand canonical partition function has as its natural variables alpha and beta. The canonical partition function has as its natural variables beta and n. And the entropy has as its natural variables n and u. So it works. Each corner has as its natural variables the neighboring sides of the square. Secondly, when we take the partial derivative of a corner with respect to a neighboring side, then we move to the opposite side. We get the conjugate. Up to a sign which depends on whether we start at the tail or at the head of an arrow. Let's check that in the example of the grand canonical partition function. We take the partial with respect to alpha, and then we move to the opposite side of alpha, which is n. So the partial of the log of the grand canonical partition function with respect to alpha gives n, with a positive sign because the alpha is at the top of an arrow. And you can check it for all the others as well. It works. And then a final information that we can glean from this Guggenheim square: when we move from one corner to another along an arrow, parallel to an arrow, then we add the product of the two ends of the arrow. So, for example, moving from the log of the canonical partition function to the log of the grand canonical partition function, right, in order to go from the lower left to the top left corner, we move along this arrow, this vertical arrow, parallel to this vertical arrow, and so this means we have to add the product of alpha and n. And indeed, our formula said that the log of the grand canonical partition function is the log of the canonical partition function plus alpha times n. So this is also in this Guggenheim square. Or if we want to calculate the entropy, starting from, again, the log of the canonical partition function, we have to add the product of beta and u, because we're going parallel to the horizontal arrow. So it's all the relations that we found in this chapter are encapsulated in this Guggenheim square. The top left corner, this is the grand canonical case. The lower left corner, this is the canonical case. And in fact, the lower right corner, This is when you work in the microcanonical ensemble. When you work in the microcanonical ensemble, then what do? You have up to some finite measurement accuracy. You have both particle number and energy given as sharp values. The energy up to some measurement uncertainty, delta U. And then all microstates that are compatible with this energy constraint are equally probable, equally likely. So, and each of these microstates, these allowed microstates, is assigned the probability 1 over the total number of allowed microstates. And remember from our discussion of entropy, when you have a probability distribution where all states are equally likely, you have a uniform probability distribution, then the entropy over K is simply given by the log of the number of states. Or in a random experiment, you have n possible outcomes. All outcomes are equally likely. You have a uniform probability distribution. Then the entropy of this distribution is the log of the number of outcomes. That's what we found when we discussed the entropy. And the same here in the microcanonical ensemble. You have allowed microstates that satisfy the energy constraints. They are all equally likely. And the associated entropy then is simply the log of the number of allowed microstates. When we call this number of allowed microstates capital W, then we find that the entropy over K is nothing but the log of this W. And you can view this W as the microcanonical partition function. So in fact, this lower right corner here corresponds in this sense to the microcanonical ensemble. Now we've proven together the equivalence of the grand canonical and the canonical ensembles. If you want to prove the equivalence of the canonical and the microcanonical ensemble, the argument proceeds in exactly the same way. And I encourage you, and maybe this is actually going to be one of the next homework problems, to do that, to recapitulate the same logic to show that equivalence as well. Now, just for completeness, I want to write down that all these relationships hold only in the thermodynamic limit, and that entailed homogeneity, stability, and size becoming very large. So this is important to remember, that you can apply this Guggenheim square only in the thermodynamic limit. Now we are at the end of this discussion of the equivalence of ensembles, and I just want to remind you why this is so important and also so useful, because as I had said at the beginning, this allows us, when we want to tackle a problem in statistical mechanics, it allows us to pick the most convenient ensemble, most convenient in terms of calculations. Once we've convinced ourselves that these prerequisites are in place, we have the thermodynamic limit, and then we simply pick the ensemble with which it is easiest to calculate.